Hi, welcome back to Elasticity. Today we are going to talk about a very important aspect of elasticity, which is to find the components of stress on different faces. Our task is the following. I know the components of stress on two perpendicular faces. How do I find them on another face? What do I mean by that? What I mean is the following. So I'm going to pick my coordinate system to lie along the two perpendicular faces. That's not a big deal, right? So I know the stress on this face and I know the stress on this face. So normal stress sigma xx is known. Remember our notation. Sigma xy is known. Sigma yx is known. Sigma yy is known. The question is, what about this face? I want to find out sigma nn is what? Sigma np is what? N is the normal. Okay, you have probably done this using Morse circle, but today I am going to show you a matrix version of doing this in a fairly simple way. The reason for switching from Morse circle version to a matrix version is that the matrix version works also in 3D. Morse circle works only for plane problems. The matrix version works for 3D, and it's actually fairly simple. It uses equations of equilibrium and basic algebra and some version of limits. We are not going to be very careful about our proof because luckily the proof works and we know the answer, so we can do a slight shortcut in the sense that we won't do the proof very carefully, but our ideas will be all okay. So let us see how to do this. We start out by drawing a free body diagram of a triangular piece. So I'm going to draw this here. So there is the triangular piece. The normal to this thing is like that. Okay, and that's x, sorry, that's y, that's x, and our normal is going to be calculated that way, theta, counterclockwise from positive x-axis. If you always do all your angles this way, you don't have to worry about which signs are what. Cos theta, sin theta will all work out very well. So the normal vector will have component nx in the I direction, ny in the j direction, both of them negative. You can see that the normal is the third quadrant. And that will turn out to be cos theta I plus sin theta j. You're saying, hey, wait a minute, what about sines? That's the beauty of measuring theta from the positive x-axis. Theta is more than 180 degrees, so both cos theta and sin theta are negative. So we don't have any problem. T, the tangent to this face, looks like that, and T will look like minus sin theta I plus cos theta j. The reason is it's because it's 90 degrees from n. That's all. You just do that, you get n and t. So this will be tx, this will be ty. Excellent. Now we're going to draw the free body diagram. So I'm going to draw the forces. So let me draw the known forces. Presumably I know fx. This x represents the face. I know fy, but what I don't know is fz, sorry, fn. Okay, so from equations of equilibrium will tell us that the following is true, right? Fn must be equal to minus Fx minus, sorry, I'm going to write that as Fy. No biggie. Agreed? Excellent. So what we are going to do now is divide by An, which is the area of this face. Because, why are we dividing by An? Because we are interested in force over unit area. You are with me? Force per area. So I have to divide by An. So that will give me Fn over An equal to minus Fx over An plus Fy over An. This one is okay. These two are not okay. What do I mean? I am dividing by the wrong area for that. Can you see that? What I really need to do for Fx is divide by this area, for Fy to divide by that area. You see what I mean? So I want to do that. I am going to do a very clever trick, which is to write this as Fx over Ax over An plus Fy over Ay over An. That's all. Thinking, what's the big deal? Now comes the beautiful trick. Turns out that by looking at the trigonometric aspect, trigonometry will tell us that minus Ax over An equals Nx, that is cos theta, minus Ay over An is sin theta, Ny which is sin theta. How cool is that? Turns out to be generally true, by the way. If you take a tetrahedron with faces on that side, An will be Ax Nx plus Ay Ny plus Az Nz, like that. Okay, and you can do sorry, I got to rewrite this. Ax is An Nx, Ay is An Ny, Az is Az Nz. So this is a nice result purely based on geometry of triangles. There is nothing more to it. Okay, so what does that give us? It gave us Fn over An equals minus Fx over Ax, sorry, yeah, that's right, Nx plus Fy over Ay, so there is no more minus here, that has become plus because of this, plus Fy over Ay Ny. So this minus sign is hidden in Nx and Ny. You with me? So now this is all very nice, but we know what is Fx over Ax, right? We did that before. This turns out to be force per unit area on face X, which is equal to sigma xxi plus sigma xyj. It's very nice. Similarly, Fy over Ay will turn out to be sigma yxi plus sigma yyj. Oh, very nice. So now what has happened is force per unit area on face N equals sigma xx nxi plus sigma xy nxi plus sigma yx nyi, sorry, this is j, plus sigma yy nyj. Thinking, man, that's a big mess. It's not a problem because matrix algebra to the rescue. So if I write I component j comp will turn out to be sigma xx, sigma yx, sigma xy, sigma yy, nx, ny. So this matrix multiplication will tell us I and j components of the force per unit area. Technically we are done, but you go back here and you say, was that what we wanted? What we wanted were sigma nn and sigma nt. What we got were sigma nx and sigma ny. So this is actually x and y components. We didn't get the sorry about that. Yeah, there we go. So what we got is sigma nx, sigma ny. I think who cares about sigma nx, sigma ny? I want sigma nn, sigma nt. So how am I going to get that? That's easy. If I remember, if I want to calculate the component of a force in a direction, what do? I take the sigma nx, sig I plus sigma nyj and dot it with nxi plus nyj. So what will that give me? That gives me a very nice result. Sigma nn equals, this is the most important thing, nx ny, sigma xx, sigma xy, sigma yx, sigma yy, nx ny. Nice matrix multiplication. This is the same as Morse circle in 2D. The thing is, you can extend it in 3D. It's not a problem. In 3D, the reason why I am writing this in red is because these two results are important. Okay, these results are important. So I'm going to write that sigma nn equals nx, ny, nz times sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz times nx, ny, nz. That's all you have to do. Just matrix multiplication. You have a MATLAB, this is easy. Most calculators, it's trivial. Okay? You don't have to remember all this cos 2 theta, sin 2 theta. Anyway, it does not work in 3D. You're thinking, okay, we found sigma nn. What about sigma nt? That's easy. That's sigma nx I plus sigma ny j dotted with tx I plus tyj. Hey, all I have to do is replace this. So I'm going to write that, which is tx ty, the components of the tangent direction, sigma xx, sigma yx, sigma xy, sigma yy times nx ny. This tells you the phase, this tells you the force. You're with me? That's how it works. This is my stress matrix. You can combine all of this into a nice thing. You can write sigma nt, sorry, sigma nn, sigma nt equals nx, ny, tx, ty times sigma xx, sigma yx, sigma xy, sigma yy times nx, ny. Phase force. That's all you have to do. So this is just equilibrium plus geometry. How nice is that, right? Just equilibrium and something about the areas, that's all. Equilibrium plus geometry will give you this. The point is, we made several simplifications. One, no gravity or other body force. Second, no acceleration in our proof. But it turns out, by taking limits, Cauchy is smarter than this. He showed that it will work even for these cases by adding calculus. Limit as the triangle shrinks to 0. So by doing this and taking limit as the triangle shrinks to 0, he was able to show that. We are not going to show that because it doesn't particularly add any deep insight to us. All it tells us is this result is true whether the body is accelerating, whether there is gravity, body force, this, that and the other, although our limited proof was only for no body force and no acceleration. Okay, so the question is, how do you use it? So imagine the following question. Okay, given seven megapascals, 8 megapascals, 7 megapascals, 4 megapascals. Stress. Find sigma nn and sigma nt at 30 degrees to the x-axis. That's easy. So first thing, let us figure out the phase. Nx equals cos 30 degrees, which is root 3 over 2. Ny is sin 30 degrees, which is equal to half. Tx equal to minus half. Ty equal to root 3 over 2. So we are pretty much done, believe it or not. These we have to rewrite in a matrix. So this is x phase. So sigma xx equal to 8. That. Sigma xy equal to 7. That. Sigma yx equals 7. This. Sigma yy equals 4. That. See how it goes? Then multiply that by root 3 over 2 half And then this side, you get a bigger matrix, root 3 over 2, half minus half, root 3 over 2. This is N, this is T. So this is force phase. You just do this matrix multiplication, there's no biggie, and it will turn out you will get 13.06 and 1.76 megapascals. That's all. So if you remember this phase the force, and remember the phase components go here, the direction components for the force go there, and matrix, stress matrix goes here. So stress, normal components, direction components for different forces. That's all. So if you remember phase the force, you can do any of these things. It's not a problem. Thank you. Bye.